All right, thank you. Thanks very much. My apologies for two apologies. One apology for not being there at Vienna, where I studied some time ago. I actually studied at Boltzmann-Gasse and had many impressions from there. Second apology, I'm just a physicist, so I am Erdős as everybody, but I'm only a physicist, so please be gentle with me because I may not express everything correctly. So what I will speak about is about the mother of all packing problems, of all hard disk problems, of Markov chains, the mother of two-dimensional physics. And listening to the very interesting talks over the week, at the end, I decided just to tell my story, which is at the interface of things that are discussed here in the meeting and that work on. And here is the list of collaborators. I will speak about the very recent paper that came out at the end of last year on arXiv. So let me continue with the start with hard disk packings here. Excuse me, I'll have a few different language slides here. So this is the famous paper by Fejes in 1940, proving the optimal disk packing in 2 dimensions. And again, I just want to say I'm actually at the present I'm preparing a review on hard disk system. So I heard a lot about that. There's another paper. So I understand the Fejes proof of why the hexagonal packing is the optimal packing. People say that there is a proof by two-way, but it's wrong. Conway and Sloan speak almost like physicists would do. They don't actually say it's wrong. They say a long history. So I have a question to the audience. I really need to understand whether this two-way proof is true or not. Unfortunately, when I send messages to some of you, even someone in the audience, I don't get an answer. So maybe somebody can help me from this very, from this community, from your community, and tell me whether this 1910 proof is correct or not. So here's my second talk, my second slide, and it's about it's another paper from 1964 by Böröczky, a Hungarian mathematician whom I came to appreciate very much. Also written in some approximation of German, as you can see in this green thing here. And this is the paper that shows that sparse, locally stable packings exist in 2 dimensions and also in higher dimensions. So that means that it's not the closest packing, but it's also a packing, and it's a packing that has very, very low density. And very recently, we were taken to move in the footsteps of this paper. We provide open source arbitrary precision implementation. And one of the stories I want to speak about in this talk is that we use this as some kind of Poorman's version of mixing. So we ask ourselves how the Markov chain Monte Carlo algorithms that are of very great importance, as I will explain, can wiggle out of these configurations, and we use this as a figure of merit for the algorithms, because we are unable, as everybody else, we are unable to compute decent mixing times for these algorithms. So here you see just a figure out of our paper, a Böröczky packing with a core, or 2 Böröczky packings with a core and with kind of arms going out. And now here it has five layers, and you can make them as much as possible. And then the density will scale like 1 over the number of particles in your system. So that's a packing. So now here I have 2 types of that I combine on one slide. The 2 types of hard disk packing. On the left side is it's the densest hard disk packing, proven by Fejes, 1940. And on the right side, you see a square. Though this is a square, and in the square you have this little cross, and this little cross is one of the Böröczky packings taken out of our open source, open access software with 100 layers in this thing. So these 2 packings are of course very different, because one has the highest density, another one has a almost zero density. That means zero packing, zero number of spheres, zero fraction of space covered by spheres, whereas the other has the highest density. But they share two properties. One of the property is that they have long-range positional order. So you all understand that you can Fourier transform the positions here in this the positions of each disk, and then you get what we call in physics, we call Bragg peaks, and you get regular structure. So you have long-range positional order, but you also have long-range orientational order, which means that you can take the orientation of two disks up here on the lower left sides, or you can take the mutual orientation of three disks here, and you can compare the mutual correlation of three disks very far away on your system. Imagine you do this in a very, very large system, and you see, of course, that the correlator of the orientational order, just as the correlator of the positional order does not go to zero. So you have these are configurations with long-range positional order and long-range orientational order. And this is true both for the high density and for the low density packing that I showed you. So let's continue. And of course, where I kind of depart from the subject that was of very, very big or is of big interest for the workshop, is that I go away from close packing. I go away from the situation where disks actually hit each other. So what's happening in this situation where you, for example, you take your system almost at close packing, and then you increase the space in which they live by such that the overall density in the limit of n going to infinity is no longer the close packing density, but is a finite amount less than this close packing density. And here is another very famous paper by Rudolf Peierls, translated into French. It came out in the Annales de l'Institut Henri Poincaré. And it's this paper that is very often credited with having shown that in 2 dimensions, any finite density system of hard disk can no longer have order. Well, if you read through the paper, which is openly accessible, you'll see that it never mentions 2 dimensions, but it makes a point. And this point I have underlined it or highlighted here in the picture, is that there's a qualitative distinction between a solid and a liquid. In fact, there's a qualitative distance, as we would say today, between a crystal and a liquid. And that this qualitative distance can be obtained in 3 dimensions. But if you looked at the same system in 1 dimension and also in 2 dimensions, you see that there cannot be any long-range positional order, so that the difference between a solid and a liquid disappears. And what this means in more fundamental terms is that this very nice picture of orientation, as I have it here on the left side, breaks down immediately in the limit of if you relax the condition of being at the smallest volume that you want to have. The way you prove this, or that the way, not prove, excuse me, I shouldn't pronounce the word prove, but the way you understand this is you replace these hard disks or these particle systems with systems that with a system of springs. So you connect this particle with this particle with a spring, this particle with this particle. All the neighboring particles are connected with springs that are fixed, and then you end up in a harmonic model that you can solve exactly. And this harmonic model shows already that you don't have that you don't have long-range positional order. And in 2 dimensions, but you can have that in 3 dimensions. So now I make a big leap into, first of all, I show an English language paper, but this is a very, very famous paper by David Mermin from 1968, who makes exactly the same point again, that you cannot have a crystal in two-dimensional particle systems, more generally than for just for hard disk, but you cannot have long-range positional order. But then he makes the point exactly on the system of in a harmonic approximation, and he says that if we look at the harmonic approximation of the two-dimensional hard disk, so the harmonic system differs from the real particle system in the fact that, just like in the bed spring, the connections between particles are fixed once and for all. But he made a point after people had studied this harmonic system for decades. He found out that it is more complicated. So of course he found out as anybody else that it doesn't have long-range positional order. But then he looked exactly at this kind of Zweibein of he looked at how do a particle connecting on one side of the system and two particles connecting on the other side. Here you have the correlator. How do they correlate? And he found that the correlations increase like the logarithm of r minus r prime for r minus r prime to infinity. So he understood that if you make the slightest change to the hard disk packing in the harmonic approximation, of course, then you lose the positional order, which was already known, but you retain long-range orientational order, and the particles will be oriented all through the system the same way. So this was a groundbreaking understanding, but of course it's only in an approximation to a theoretically important system. So now let me take on the second part of what I had in my title, Markov chains. So what is actually happening in these systems at finite densities? So what was actually happening until today, there is, as many of you may know, until today, there is no proof. There are very, very few proofs. The only thing that is proven is that at low density, the system is a liquid. It has no orientational order, has no positional order. And this, there has been much recent progress in this field, because very recently it was the first Monte Carlo algorithms with proven mixing times have been devised, and one of these algorithms was proven to have fast mixing, and now very recently Helmut et al. 2 years ago showed that because it was fast mixing, it had to be a liquid. But it started, of course, a long time ago with this very famous paper by Metropolis et al. 1953, one of the most cited papers in all of physics, which came up with the Metropolis Monte Carlo algorithm exactly for the system of two-dimensional hard disks. So here you see it. They have a general method computing the equation of state. I'll go into this, what this means, the pressure as a function of volume for substances consisting of interacting molecules. So this was used for hard disks. And here the results for the two-dimensional hard disk system have been obtained and are presented. So what is this algorithm? This algorithm is, of course, that you take one particle at a time, you move it a little bit, and if you can move it, you move it to where it wants to go. If you cannot move it, just like here on the slide number on the frame number 4, if you cannot move it, you stay where you are. So this is the famous Metropolis algorithm. It introduced, it's the first paper on Markov chain Monte Carlo. It's the first paper on reversible Markov chain Monte Carlo. And it's also the first paper on non-reversible Markov chain Monte Carlo, as I can explain to you if you are interested. But as I showed in the abstract, or as they showed in the abstract, they announced results. And the result that they announced, I have it highlighted here in red, is that there is no indication of a phase transition. So there was no indication of a phase transition because, as I told you before, the gods of physics, Peierls and also Landau, David Landau in the 1930s had shown that there could not be long-range order, long-range positional order. So there was nobody expected a phase transition, and it shouldn't just happen. So it was clear that nothing could happen. So the picture was that the system will remain in all dimensions a liquid from zero density up to close packing density. And at close packing density, all of a sudden, it would become a crystal. So then, now I'm moving from 1953 to 1962. In this also one of the most outstanding papers in all of computational physics ever, Alder and Wainwright. And they did a system of 870 hard disks, and they came to another conclusion. And this other conclusion was also that although the physics that is explained here in my yellow question mark, it's not a van der Waals loop, but doesn't matter. So they came to the conclusion that this system had a phase transition and went from a liquid to a solid. So now, please interrupt me if you have questions, of course. So it went from a liquid to a solid. So very recently, we have been interested in revisiting this problem. And of course, these calculations, so the Alder and Wainwright calculations were done with molecular dynamics. So not by Monte Carlo method, but by solving Newton's equations of motion, but the outcome is proven to be exactly the same. And the conclusion they came to is shown here on the left of the picture. And here you see the pressure. So I don't have time to actually explain to you what the pressure is, but just imagine if it wasn't a system with periodic boundary conditions as we have it here, then it would be simply how the particles are banging onto the walls, and it would be just a pressure, just very similar to what you do if you blow air into your in a football or into tires. So they computed the pressure in a system of fixed volume and found this equation of state, found that the pressure was not, so here going to the right you go to low density, going to the left you go to high density, and the infinite density is the maximum packing is up somewhere up here. And they found this loop, the loop that they call a van der Waals loop, that is not a van der Waals loop, but they found this loop and indicated that this was a phase transition. So here we just redid some of these calculations. So these calculations were done in a box with periodic boundary conditions with specific ratios of the length to the width. And here you have a liquid, so which connects to the liquid that is proven to exist in the limits of vanishing density. But if you go a little bit higher, then you have something that looks like a crystal. But it cannot be a crystal as I showed you before, because it cannot be a crystal, but it can be a solid. So that's what they showed. And here we just, in this little inset on the lower part to the right, you see the original data that we just recently scanned, because we are approaching the 60-year anniversary of this paper. You see the 870 particle systems in a box of size 29 by 30 square root of 3/2, whatever the details. And you have the original data from 1962 in blue. And now you have high precision Monte Carlo data that we obtained with our much more evolved Monte Carlo algorithms. And the only thing that you can observe is that they are exactly the same. So this is, of course, not rigorous math as we would all like it, and as you do it, and I would also like to do it, but it's not rigorous. But it's quite amazing that 60 years after this original paper, you can redo these calculations, and you find with an error bar of 10⁻⁵, you find exactly the results for the pressure as a function of volume as they did 60 years ago, which is, of course, one of the reasons why this is such a great paper, because the conclusions were outstanding, but the basis on which it was formed was just rock solid and can be verified even today. So now this is another representation. So at low density you have something that has no order, At very high density, you have something that has order. And the story didn't end. In fact, it continued for many decades later, because people were interested in finding out what exactly was happening at this transition. And with all that I explained to you from the beginning, there are a certain number of things that can happen. First of all, nothing could happen. So it would be that as I said, you have a liquid. So liquid, what it is that you have positional order. So you take one particle, you take another particle, you check them, and you check whether they are approximately on a lattice or whether they are not on a lattice. And if they are not, and if the correlation functions with which you lose this order are short range, then you have a liquid, and they are, as you have the positional order and the orientational order is short range, and this is what is proven to exist at low density, at low finite density. Then, as I explained to you at the beginning, the solid cannot be along at finite density, except at the point of close packing, cannot have a long-range positional order. It's just not possible. So it cannot have long-range positional order. And so, but what can happen following the paper by Mermin, 1968, it can have algebraic order. That means that the positional order decays, but it does not decay with a length constant as in the liquid, but it decays algebraically. So that's the solid. That can happen, of course. And then there can be a third phase, and this third phase is the intermediate between the solid and the liquid, and it's the hexatic. It's called the hexatic. It has short-range positional order, so the particles lose their positional orientation, their positional order quickly, but they have an algebraic. That means a power law decay of orientational order. This hexatic phase is something that is very common in liquid crystal systems. Liquid crystals is the ones that we have that we used to have on our wristwatches, on liquid, but so this is something that is known to exist. But in the hard disk system, it was in two-dimensional particle systems in general, it was for a long time, it was discussed whether this hexatic phase existed and whether the transition was as first proposed by Alder was from the liquid to the solid, or whether it was from the liquid to the hexatic and to the solid. So here also intermediate, as something I have to explain to you in very briefly. It's the Kosterlitz-Stauler's phase transition, which is the underlying physics, is how you can have a phase transition without actually going from a liquid to a crystal. So the first page of this is a Nobel Prize winning paper from a few years ago. I mean, the Nobel Prize from a few years ago, and this Nobel Prize paper explains exactly the same story as I did. And so it tells you the story about piles, and it also tells you that there's evidence from Alder and Wainwright telling you that something has happened, but even though you cannot have a crystal. So now one of there have been for many decades, there have been two ways of doing numerical calculations. One is the solution of the equations of motions, Newton's equations of motions, which is called molecular dynamics. And the other one is Monte Carlo. And as the Monte Carlo algorithm had been invented for these systems of hard disks, it had never been changed. The algorithm that was used is the one that I flashed in the beginning. I can go back to it. You simply take one disk, you move it by little epsilon, and then as time continues, you move by little epsilon all this. And this was the only algorithm that was known, and that was imagined. It was extremely difficult to find other algorithms. For example, you may know that in Monte Carlo calculation in spin systems, there are much more advanced algorithms called cluster algorithms, but they could not be used. in these systems, or in particle systems, the systems that you are interested in. These cluster algorithms usually don't work, so you are stuck with local algorithms where you move locally one particle. So just in very similar to what Carlos Beltran just explained in a greedy way, but you just do it you do it randomly. So fortunately, a few years ago, we came up with a new class working together with Etienne Bernard and David Wilson, mathematician from Microsoft in Redmond. We came up with a non-reversible continuous time Monte Carlo algorithm that has been the starting point of an enormous class of algorithms that do infinitesimal moves, just like the Monte Carlo algorithms of Metropolis et al. They do infinitesimal moves, but they are non-reversible. So the original algorithm that we came up with is you take one disk, you move it by a little bit, just like the one that I have here. You move it, so you move it in continuous time. In fact, that's the interpretation that we came up with at the end. So you move it in continuous time until one of its neighbors is unhappy with the move. At that moment, this disk stops moving, and this one moves until one of its neighbors becomes unhappy, and then continues until one of its neighbors becomes unhappy, and then stops here. So this continues, this continues, this continues. You move in X direction, and then you move in Y direction. And we made a number of observations. First of all, this algorithm, so I hope you understand the way you go it. For example, just to show that it's not a detailed balance algorithm, is you always move to the right, and then you move up with periodic boundary conditions, but you never have to move backwards, and you never have to move downwards. And you have to, and you can do this because you can prove that although this algorithm violates the detailed balance condition, it satisfies all the laws that Markov chains have to satisfy, in this case, a global balance. So it satisfies balance with the uniform probability distribution in the space of configuration. So as I explained to you in the beginning, this is an algorithm where you move until it hits the other particle. But in fact, if you want to generalize it to very different systems with many different interactions, pair interactions, three-party, whatever. So the way it works is you move until it finds one particle that is unhappy with what it's doing, and then lets this other particle that is unhappy continue moving and doing what they have. So we have generalizations of this algorithm for smooth potentials, for potentials that cannot be expressed as pair potentials, and so on and so on. And in the last few years, there have been a number of variants of this algorithm: straight algorithm, reflective, forward Newtonian event chain Monte Carlo algorithm. So what we would really like, and I'm now coming to the punchline of my talk, what we would really like to have is we would really like to be able to compare the mixing times of this algorithm, compare the mixing time of this algorithm with the mixing time of Metropolis algorithm, and so on and so on. But of course, these are very complicated systems for which we cannot actually evaluate the stationary distribution. We have many problems, so we are really in a poor man's situation. And at the end, I will just show you one attempt where we try to not compute mixing times because it's just too complicated, but where we try to quantify the escape times from these Böröczky configurations. I'll show you. So in any case, all of this, so this non-reversible continuous time Markov chains have become a whole new world. I just recently wrote a review on this subject. It's a new world that unites workers from statistics and from theoretical physics, as I am. We work on the same problems, and we discover a whole new world where you end up where the stationary distribution towards which all irreducible aperiodic Markov chains converge to are no longer they are the equilibrium solutions in a physical sense, but they are found in a way where you don't have equilibrium at all. You move all the time, so you look at these configurations as they go on your computer, and all the time you have motion in some directions. For example, in this algorithm, you have motions to the right, you have motions up. So you approach the steady state is no longer an equilibrium state, as it has been the tenet for more than 50 years. So with this, for example, we were able to compute, for the first time, actually take very large systems. So for example, here, 1 million particles through the whole density. And we were able to compute this equation of state, pressure as a function of volume, and obtain data that shocked 10 years ago, that shocked the community, because there was, as I told you, there were lots of discussion of what was happening. But in fact, what we found out is that something was happening that was not at all foreseen. So that this hexatic phase of the intermediate ordered phase actually existed, but that the transition from the liquid to this hexatic phase was a strange transition. And actually doing this calculation required new algorithms, and the one that I just explained to you. So then we also have, as I told you, these algorithms can be generalized to soft disk particles. And so the soft disks means we have, in your language, it's point processes, but they are no longer point processes with a hardcore interaction. The interaction here is what we call a soft disk interaction 1 over r to the power of n. So the limit of n going to infinity is the hardcore limit. And any finite n is different. And so in all of these cases, as I showed here in the picture with in a paper with Sebastian Kapfer, is that this liquid, in all cases you have liquid, hexatic, and solid phases, but the type of transition changes as a function of n. So again, so these scenarios can be computed. They can be computed with the modern algorithms much better than before. So now, in the end, I would like to, of course, I want to explain. So I want to come back to the packings, and I come back to these Böröczky packings that we were able to look at. And so these packings, of course, strange. They are called stable packings in the original papers, but they are also, of course, they are only locally stable. So here you have one of these packings one of these packings, and because they have less, so we have a system of n particles living in 2 dimensions. So you have 2 n constraints, but you can of course see that you only have of the order of n, a little more than n constraints in your system with this, in a system with 2n degrees of freedom, which means that you can have collective modes, and I've shown you 2 collective modes here that get you out of these configurations. So they are stable, but only locally stable, and they're not really jammed. In some other language you call these, they are not really jammed configurations, but they do pose a problem. They do pose a problem for the local Markov chains that we are using, because the local Markov chains that we are using, the Metropolis algorithm with a small step width, or these event chain Monte Carlo algorithms that move just a single particle at each time step, they are trapped by these configurations. And unfortunately, it's just a matter of fact that these configurations exist at any density. So these packings, they trap local Markov chains that move single disks. So now we are in a lot of trouble, unfortunately, because I was hoping to come to talk to you, and that I could actually get help from some of you. Of course, I understand that the space of these trapped configurations of these packings is a low dimensional space. It's not a 2n dimensional space. It's a much lower dimensional space. But I must say that I'm quite confused about whether these configurations are fundamentally problematic, because maybe they can can they break the connectivity of sample space? So these are the points that I would have loved to discuss, but we'll just do this at some other point. So now the situation is is more, let's say, we can have a more practical point of view. So we take from these Böröczky packings, we go to something that we call epsilon relaxed configuration. So configuration is something where disks don't touch. So we just take this original packing. We reduce the radius in the original packing. The radius is 1, and in a configuration epsilon relaxed configuration, the radius of each disk is only 1 minus epsilon. So it's clear that if you are at 1 minus epsilon, then your local Markov chain that we are actually interested in, that we actually want to get results from, they can move out and they can wiggle their way out of these configurations. And this set of somewhat relaxed, if you don't relax everybody with the same epsilon, if you don't relax everybody and leave them at the position. So here in the picture, I left everybody exactly at the position, but you can of course move them by epsilon. And you understand that now we have a finite portion of sample space in which these epsilon relaxed configurations live. You can decorate them with other particles, so you can get them also to higher density. And for a small epsilon, these relaxed Böröczky configurations are tough cookies. So they are really tough configurations to get out with. So this is, of course, unfortunate, but it's also fortunate in a way, because we were able to obtain exact scaling predictions to how much time it takes, time measured in events in our event-driven algorithm, but that's not really important. So what we are actually doing now, I'm at this poor man's version of what I would like to compute, namely a mixing time. So we compute the escape time with some kind of criterion. So we start in this Böröczky packing. We reduce the radius by epsilon. And then we wait until this configuration has dissolved. And then we do this here we have 2 different cases, but we do this for the Metropolis algorithm. We do this for one version of the event chain Monte Carlo. And we do this for another version of the event chain Monte Carlo. And we see enormous differences in the time that takes out, takes you to get out, and one is like 1 over epsilon, and the other one is just logarithm of 1 over epsilon. And of course, we see this behavior in the behavior. We have to see this in the behavior in our real applications, which are not these Böröczky configurations, but we see them also in the real life. And so we're also quite happy because we have so these epsilon to the minus 2/3, epsilon 1 over epsilon, logarithm epsilon, they are not fitting parameters, but they are predictions of a scaling quote unquote theory, which is not an exact result, but we think we understand why some of these algorithms behave like epsilon to minus 2/3, and some of these algorithms behave like logarithm of epsilon. So I just want to say that this escape time is measured in trials or in events. Maybe we can go like, so there are enormous differences in escape times between local Metropolis algorithms and these modern non-reversible Markov chains. Enormous difference in escape times also between the different variants. And this will give us a lot of work for the coming times, because we want to understand whether we can find these in real life applications. So now the last point I want to make is a general point on the relevance of packings. And of course, the packing is something that can be related to an infinite pressure configuration. So this is maybe a little bit paradoxical, because I computed equations of state. That means pressure as a function of volume, and the pressure was always finite. So what does it mean that the system is infinite pressure configuration? It means that you can have simulations, or you can have ensembles in statistical physics. One is where you have a fixed volume. This is called the NVT ensemble. T is temperature. Temperature doesn't play a role for hard spheres. So you have the NVT ensemble, or you have the NPT ensemble, where the system, given one configuration, simply can blow up. You can blow up by something called a homothetic expansion of the box with scale. Everything scales up except of the radius of the box. And if you do this homothetic expansion, then so this would be here at for this configuration would be at its cutting volume. So at this minimum, you cannot decrease the volume. But if you use one of these algorithms that are able to do a homothetic expansion of the box, you would immediately go from a box of this size to a box of a size in which the epsilon would be. That means that the minimum distance between two disks would be like 1 over PV. So in a sense, in our application, this very small values of epsilon, and even it must be said, the existence of packings in statistical physics is quite is an arbitrary concept, and it's related only to the NVT ensemble, where you pack particles into a fixed box, and if the box can breathe, then the epsilon, the minimum distance between two disks, is typically of the order of 1 over the pressure over the volume. And this is something that we can discuss in the one. So now I come to the conclusion that I discussed packings from low density to high density. And of course, one point was that we use these low density packings as some kind of skeleton structures from which we studied how our local Markov chains escape from them. And then the second point was, of course, that I discussed some local Markov chains that had been very stable environment for decades, until in statistics, as in statistical physics, the revolution of non-reversible Markov chain came up, discussed some of the hard disk model. And I just, as a final reminder, I need help to understand what happened with this Tool paper. With this, I would like to thank you for your attention.